Hey guys, so we're continuing with log and exponential functions. Now it sort of all culminates in 4.5. So within 4.5 we're going to discuss how to solve exponential equations and logarithmic equations. You're going to need to combine all the information that we learned in the prior sections for chapter 4 in order to be able to sort of get a complete picture. Within this section, I'm going to actually go over a bunch of problems, mainly because this is the more important of all the other sections, and that it puts everything else together. So within 4.5, we're going to learn how to solve exponential equations and logarithmic equations. It's going to be not a similar process, but we're going to see that we're going to need exponential equations to solve logarithmic equations, and we're going to need logarithmic functions to solve exponential equations. So what's an exponential equation? An example, something like, let's just have 3 to the x plus 2 equals 7. So how would we solve 3 to the x plus 2 power equals 7? I give you a 3-step process. Isolate the exponential expression onto one side of the equation. Take the log of each side and use the law of logs to take down the exponent and solve for the variable. So the whole point of an equation like this is to solve for x. Now how do I find x if it's in a power? 3 raised to what power is 7? It's not a straightforward question. I know 3 to the 0 power, anything to the 0 power is 1. 3 to the first power is 3. 3 squared is 9. But 3 to what power gives me 7? It's some weird middle zone. I'm going to use the 3-step process, which is on slide 80. You guys have it in your notes. Isolate the exponential expression onto one side of the equation. That's already done for me. 3 to some power is already all by itself on one side of the equal sign. Nothing to do. Take the log of each side. So this is interesting. Just like we can add 5 to each side of an equal sign to keep the balance or the equality, or subtract a number, or multiply both sides of an equal sign by a number to maintain equality, we can do the same with logs. So to solve an exponential equation, I'm going to want to take the log of both sides. I'm going to take the log of 3 to the x plus 2 and equate that to the log of 7. Remember, whatever I do to one side, I have to do to the other side of the equal sign. Okay? Took the log of both sides of the equation. Now I see, hey look, based on rule 3 from 4.4, that rule told me I can bring the power down. Log of a to the c power is c times the log of a. So log of a to the c power equals c times the log of a. Now for any of you that are confused as to why are we not writing a base? Well, I could take the log to the base 10 of both sides, log to the base e of both sides. It doesn't really matter. And log to the base 10 is not written. Common log, we just write log. I'm going to use log to the base 10 here because I don't have e's anywhere. If I had log to the base e or ln, that I would use that whenever I had an expression with e's. We're going to see that in another problem. So this x plus 2 can actually come down, and I have log of 3. X plus 2 times the log of 3 should equal the log of 7. Now I could divide both sides by log of 3, and I get x plus 2 is log 7 over log 3. Now please do not make the common mistake of saying, hey look, I can now use rule 2 when we combine logs and say log 7 over log 3. Oh, that's rule 2. Log of a over b is log of a minus log of b. That's not what I have here. I don't have log of a over b. I have log of 7 over log of 3. I have two separate log of functions, not log of a fraction. So I need to actually evaluate log to the base 10 of 7, log to the base 10 of 3, which my calculator can do for me. Turn it on. We do log to the base 10 of 7 is just a common log. We hit log 7. Then we divide that by log of 3. I get 1.77. So x plus 2 is 1.77-ish, approximately 1.77124. Subtract 2 from both sides, so just answer minus 2. And I get x is negative 0.23 approximately. And that's my answer. So to solve an exponential equation, I used logs, or I used logarithms. Let's check out number 2. I have 8e to the 2x. 8e to the 2x equals 20. So here, similar scenario, right? I want to isolate the log expression, the exponential expression, which I already did. I'm going to simplify it a little bit though. I want to divide by 8. So that I get e to the 2x, 20 divided by 8 is 2.5. Right? So e to the 2x is 2.5. Now, how am I going to solve? How am I going to solve for x? E to 2 times what number is going to give me 2.5? I know e to the first power is 2.718, whatever that weird number was. But I'm not going to sit there and plug and chug till my face turns blue to figure out what x is. We can use this 3-step approach by taking the log of both sides. Now, since I'm dealing with e, and I know that log to the base e is called the ln, I'm going to take the ln of both sides. The ln of e to the 2x equals the ln of 2.5. Now we're going to see why we choose to do this in a second. Why am I using ln? We'll see. When we have e's, why does it make sense? When we have the natural exponential function, why does it make sense to use the natural logarithmic function? So what I'm going to do now is bring the 2x down. Okay? I'm going to use rule 3 and say ln of e to the 2x is 2x times the ln of e. That should be the ln of 2.5. Now, the ln of e, or log to the base e of e, if you guys remember in our properties of exponential functions or logarithmic functions, this means e to what power gives me e to the first? The answer is just 1. And we discussed this. The ln of e, when we discuss the properties of exponential functions and natural logarithmic functions rather, the ln of e equals 1. So 2x times 1 is just itself. It's just 2x. Right? So the ln of e equals 1. I don't have to write it out. After I write it out, I mean, I can just say, okay, the ln of e equals 1, 2x times 1 is itself. 2x is the ln of 2.5. X is going to be the ln of 2.5 divided by 2. So I'm going to go into my calculators and say the ln of 2.5. What is that going to equal? 0.916. Divide that by 2 and we get 0.458. So x is 0.458. Again, similar three-step approach. Start with an equation. We simplify it to a point where all we have is the exponential term on one side. Then we take the log of both sides. Here, since I have an e, I'm going to use the ln, or log to the base e. The ln of e to the 2x equals the ln of 2.5. Then I use rule 3 of expansion of logs to say the ln of e to the 2x is 2x times the ln of e. ln of e equals 1, so 2x is ln of 2.5, and the rest is calculator history. Third problem. This one's a little different. E to the 2x minus e to the x minus 6. Here, if I try to go by rule, or step 1 of the rule, which is isolate the exponential expression on one side of the equation, I could kick the 6 over, but then I have two exponential terms. And I can't really take the log of, or the ln of e to the 2x minus e to the x. Like, I can't simplify this anyway, right? E to the 2x minus e to the x, we never had a rule that said the log of a minus b is something. We had a times b, we had a divided by b, or a to the c power. So this isn't really something that we can really manipulate the traditional way. So we're going to have to do something funky. You're going to have to realize e to the 2x minus e to the x minus 6 is a trinomial. And we could actually factor this. How do we factor? Well, how do I get e to the 2x? That's e to the x times e to the x. E to the x times e to the x is e to the x plus x. Remember, same base. When we multiply, we add the powers. X plus x is 2x. How do we multiply out to a negative 6 and have a negative 1 in the middle? We have a minus 3 and a plus 2. So I can factor this to e to the x minus 3 times e to the x plus 2. If any of you don't like the factoring, just FOIL it out. E to the x times e to the x is e to the 2x. E to the x times a positive 2 is plus e to the 2x. Minus 3 times e to the x is minus 3e to the e to the x. So plus 2e to the x minus 3e to the x gives me a minus 1e to the x. Then minus 3 times plus 2 is a negative 6. Now I have these two factors, and just like, regular polynomial expressions, when I have two factors that multiply out to 0, I can set each factor equal to 0 and solve. To get e to the x should equal 3, e to the x should equal a negative 2. Now, I can solve each one of these using the three-step approach. I already have an exponential function, right? Isolated. I take the log of both sides to get the ln of e to the x equals the ln of 3. Or the ln of e to the x equals the ln of negative 2. So this is x times the ln of e, which is the ln of 3, and this is x times the ln of e, which is the ln of negative 2. Now I don't want to keep writing this out. The ln of a negative number doesn't exist. We saw that when we graphed log functions, we only had positive y output values. If you type in the ln of a negative number, you won't get a value. So we're going to end up rejecting this value. Ln of e is equal to 1. Here the ln of e is equal to 1 also, but x cannot be the ln of negative 2. We'll see that x can be the ln of 3, positive 3. X is the ln of positive 3 is 1.098. So I can say approximately 1.1. Because again, ln of e is 1, we discussed that with the last problem. 1 times x is x. And the ln of 3 we can put in our calculator and get 1.098, or roughly 1.1. Now, you could always take this answer and plug it back into the original equation. E to the 2 times 1.1 minus e to the 1.1 minus 6. Will that give me approximately 0? And it should. It should give you approximately 0. Slide 81. We're starting with log equations. So if we're going to ask you, for instance, to solve something like 4 plus 3 log of 2x. Now here we also have a three-step approach. 1, isolate the log term on one side of the equation. You might have to combine log terms. We're going to see that in another problem. Write the equation in exponential form by raising the base in each equation. So step 2, I'm going to ask you guys to add into your notes. You're going to sometimes want to use the definition of log. So to solve log equations, we're going to need exponents, and it's going to help if you remember the definition of log. We'll see what that means in a few seconds, and then we're going to solve for the variable. So here first, let me isolate the log term by subtracting a 4 out. First, I get a 3 log 2x is 12, then I divide by 3 to get the log of 2 times a number should be 4. Okay, now you think to yourself, what is this really telling me? I don't have a base written out here. So automatically you assume that's to the base of 10. Log to the base 10 of 2x is 4. Now what I mean by using exponents, I want you to use the definition of log. Remember my not so clean way of remembering it. Log to the s of e is x implies s to the x power equals e. So log to the base 10 of 2x equals 4 implies 10 to the 4th power equals 2x. So what I ended up doing is changing my log equation into an exponential equation, where my variable is not in the exponent. And I could definitely solve it. 10 to the 4th power is 1 with 4 zeros. That's 2x. So x should be 5,000. And you can plug it back in here if you want to check it. Log of 2 times 5,000 is the log of 10,000. Log to the base 10 of 10,000 is 4. 4 times 3 is 12. 12 plus 4 is 16. So it checks out. So again, we isolate the log term on one side of the equation. Then we use the definition of log to turn the log expression into an exponential equation and solve for the variable. Another problem here. So log of x plus 2 plus log of x minus 1 equals 1. Well, how do I solve this? Step 1 is going to be combining these log expressions to one log expression. As you notice, they have the same base. It's not written out, so it's the base of 10. That means I have log to the base 10 of this plus this, right? Just means that I had to multiply those two factors if I'm combining x plus 2 times x minus 1. Having written this as one log expression now, I can use the definition of log, right? Log to the base s of e is x means s to the x equals e. So log to the base 10 of this product equals 1 means 10 to the first power, 10 to the first power, s to the x should equal e, this term on the inside. Product x plus 2 times x plus 1. Now this again is x plus 2 times x minus 1, sorry. This again is much simpler to solve. X plus 2 times x minus 1 is x squared plus x minus 2. That equals 10. If I bring the 10 over, I get x squared plus x minus 12 is 0. X plus 6, x minus 5 is how this can get factored out. And I get x is negative 6 and x is positive 5. Those are two answers. Now I warn you, this is one log equation. You will have to check both of those answers. Negative 6 plus 2 is a negative 4, negative 6 minus 1 is a negative 7. You can't take the log of a negative number. So this one gets rejected. 5 plus 2 is 7, 5 minus 1 is 4. So you get log to the base 10 of 7 plus log to the base 10 of 4. Which is 1? Let me just check. No, I did something wrong. Sorry guys, backtrack. You factor out of 12, it's not 6 and 5. It's 4 and 3. X plus 4, x minus 3. So here I get x is negative 4 and x is positive 3. And that makes more sense. Either way, when I plug in the minus 4, I get rejected here. When I plug in the 3, it works. 3 plus 2 is 5, so I'd have the log of 5. 3 minus 1 is 2. Log of 5 plus the log of 2. Well, that would be the log of 5 times 2, or the log of 10. And log to the base 10 of 10 is 1. So it makes sense, it checks out. The answer is x is 3. Next, we're going to go to 82. So before we go to slide 82, I just wanted to mention, problems like this used to show up on the final all the time. You guys are have an updated sort of midterm with potentially stuff from chapter 4. A little bit of stuff from chapter 4 might spill over into that midterm. This is extremely popular in terms of, testing outside of the realm of the things that we learned before the midterm. I'd pay a heavy focus on how to solve exponential and logarithmic equations, because you also need to know how to manipulate log functions and exponential functions when you guys get to calc. So these types of problems are a favorite. You have to understand how to combine log terms, and then once you've combined the log terms, how do you use the definition of log to rewrite a log equation as an exponential equation and solve for the variables. Very popular type of question. Slide 82, applications to exponential growth and decay. So again, these are the types of problems that we've been focusing on within this whole section. A sum of $5,000 is invested at 5% a year. Find the time required for the principal to double if the interest is compounded semi-annually. So this is a little bit different. If we're compounding interest semi-annually, we have our formula A of t is p times 1 plus r over n to the n times t, where p was principal, $5,000, 1 plus my rate. What was my rate? 5% per year, 0.05. Compounding cycle is semi-annual, so 2 times a year. That's 2 times. Find the time required for the investment to double. So here we're looking for time. I do not know t. That's what makes this the exponential equation, right? Now, if I didn't know the amount and didn't know the time, this would be one equation with 2 unknowns. It would not be possible to solve. But they're asking me to find the amount of time needed for my principal to double. That means they want my $5,000 to turn into $10,000. So I know what the equals should be. I have to equal $10,000. They didn't say it explicitly, but they asked, how long would it take for your principal to double? I need to use the formula that I know that I was given to say, okay, if the principal's 5,000, double that is 10,000. First, how do I solve the exponential equation? I need to isolate the term with the exponent in it. So let me divide by 5,000 on both sides. I get 2 equals 1 plus 0.05 over 2 to the 2 times t. This is a hot mess, my people. 0.05 over 2 is 0.025 plus 1. So it's 2 equals 1.025 to the 2t. Again, how do I solve for t? Well, we learned that to solve an exponential equation, I'm going to use logs. Take the log of both sides. Log of 2 is going to equal the log of this. The log of 1.025 to the 2t. So I can bring the 2t down, and I get 2t times the log of 1.025. Divide both sides by 2 log of 1.025, because I have a 2 here and a log 1.025. T is equal to the log of 2 divided by 2 times the log 1.025. And then we take out our calculators. We say log of 2, enter, divided by parentheses 2 times log of 1.025, close double parentheses, and you get 14.04 roughly. It's going to take roughly 14.04 years if the interest is compounded semi-annually twice a year at 5% for my $5,000 to get to $10,000. Not bad, right? If I want 5K to go to 10K, it's going to take roughly 14 years. So start saving now, people. If you have the account that you're aware of that will pay you 5% interest every over 6 month periods, or compounded over 6 month periods. 5% a year broken into twice a year payments. That's part A. Part B says, what happens to this whole analysis if interest is compounded continuously? Remember, for regular compounding cycles we use this formula. For compounded continuously we're going to use a different formula, right? So I'm going to leave the answer as 14.04 years when n was 2. N was 2, the answer was 14.04 years. What happens when I compound continuously? I use A of t is PERT. So again, I need the 5,000 to become 10,000. 10,000 equals 5,000 times e to the 0.05 t. The rate is 0.05, the time is unknown. Divide both sides by 5,000. 2 equals e to the 0.05 t. How do I get the t down? I need to take the log of both sides. Since I'm dealing with e here, I'm going to do the ln of 2 equals the ln of e to the 0.05 t. Bring this exponent down. Ln of 2 is 0.05 t times the ln of e. We discussed that the ln of e equals 1. So the ln of 2 is equal to 0.05 t. If I divide both sides by 0.05 and find the ln of 2, I can solve for t. So let's see what that's going to give us. The ln of 2 is 0.69. Divide that by 0.05. 13.86. So t is 13.86. So in the second scenario, when we're compounding interest continuously and using the continuous compounding interest formula, the same rate at 5% with the same principal invested at $5,000 will give us 13.86 years time to double the money, not 14.04 years. So we're talking a few months earlier, right? This is 0.18 years. So 0.2 years is roughly, a fifth of a year. So if you think about it in terms of months, maybe we're talking 2 months. And why? Because the interest is compounded continuously. We're earning interest on interest more frequently. So we can generate the income to get to 10K a lot faster. And that's how we calculate this stuff. That's the end of 4.5. Please feel free to email with questions.